Hello everybody, this is our 18th lecture for this class, and today homework 3s are due, so if you have those I'll be picking them up a little later in the day. But we have covered the material that we're going to have covered on our test. So to remind you that test 1 is on Wednesday. On Wednesday. It will cover up to the squeeze theorem. We have established that we will have 2 study sessions. One of them I've already emphasized. So study session 1 will be on Sunday from, I think, 2 to 4. Study session 2 will be on Tuesday, and I'm open to suggestions from the 3 of you. People say, well, I can make it, it doesn't matter when it is on Tuesday.
I have class all day before 6:15 p.m. So it'd have to be after 6 o'clock. Yeah,
I have to be after 6.
6:15 until 8:15. Okay, and it'll be, both of them will be in this room.
Okay.
Okay, so that's what we'll do. Okay. And in the study sessions, I'll help you learn, memorize, go over, understand those definitions. Mainly I'll have us repeat them so we can say them, and also the known facts. And then we'll talk about it too to try to get an understanding. Well, before I move on to the new material, I don't have your homework 2 graded to hand back, but before I move on to the new material, I was curious, does anybody want to ask anything?
I've got like an abstract question.
Okay.
I was reviewing the study sheet and I was wondering, are there any systems of numbers where the completeness property or well-ordered property don't hold?
Yes. And so yes. And so for if you just have the set of rational numbers, it turns out the set of rational numbers, the completeness property doesn't hold. Okay. And so if that's your whole world, rational numbers, okay? Then it doesn't work. And then the other thing is that for the well-ordering principle, the well-ordering principle worked for natural numbers, and it said that every subset of the natural numbers has a least element. Well, there are subsets of real numbers that do not have a least element. And when we say has, we mean contains. So for the well-ordering principle in particular, if you want me to show you an example, if I just think of R.
Okay, just the whole set of R.
No, in R. If I just think of this, the interval from 0 to 1, that's a subset of R, okay? Just like we could be taking for the well-ordered principle, it says take a non-empty subset of the natural numbers, okay? Well, here I'm taking a non-empty subset of R. Does it contain its least element? Does it contain, I should say least element. Does it contain its, I guess we're saying, does it contain its infimum? And the answer is no.
Okay.
Does that make sense?
Yep.
So it's about natural numbers. That's all right with an answer? Anybody else with anything? Any questions from anybody? Ultra good to see you. I think the study session 2 announcement. Okay. All right. Well, I'm going to move on then. And what I'm going to do is I'm going to move on to talk about certain types of sequences. So this is not going to be on test 1, but we're moving on. And so the types of sequences I'm going to talk about are called monotone sequences. Monotone sequences. But we've got 2 types of monotone sequences. And the first type when we talk about monotone sequence, we're going to talk about an increasing sequence. So here's the definition. A sequence X sub n is said to be increasing if, here's the way I'm going to write it, if x sub n is less than or equal to x sub n plus 1, and that's true for all n element of natural numbers. So increasing, I'll go over that again in a second. Chuck, I want to get back to something you said. The completion property is something that's so desirable that in essence, it can be said that the completion property of R was something that we wanted to have happen, and the rational numbers didn't have it, and to make the rational numbers have it, they have to extend to include the irrational numbers, which makes all of R. So because of the completion property somebody can think of or the desire to have it, we can extend from what are easy numbers to define, rational numbers, to what we mean by all of R, that we need all of R to have the completion.
Okay.
Okay. So here a sequence is said to be increasing if x sub n is less than or equal to x sub n plus 1 for all n element natural numbers. What this is saying is the next term in the sequence is always bigger than or equal to the previous term. So the terms of the sequence are never going down. Does that make sense if we read from left to right? We'll read the sequence. Well, if we got an increasing sequence, we ought to have a decreasing sequence, and it's very similar. Here's the definition. A sequence x sub n is said to be decreasing if x sub n is bigger than or equal to x sub n plus 1, and that's true for all n element of natural numbers. Okay. We're going to look at examples of that in just a second, but before I get to those examples, let me write one more definition. So a catch-all phrase that incorporates both of these types of sequences is called a monotone sequence. So here's the definition. A monotone sequence x sub n is a sequence that is either increasing, that is either an increasing sequence or decreasing sequence. Let's look at some examples. My favorite sequence falls into one of these categories of the six we use the most. That is, this example, the sequence 1 over n. Now look at n running from 1 to infinity. Let's look at the terms of this sequence. What's the first term in this sequence, Melissa? 1 over n. When n is 1, what do I get? 1. What's the next term? All right, what's next? Right. 1/4, 1/5, Chuck. 1/6. Goes on forever in this pattern. Well, what kind of sequence do you think that is, Alfred? That's a decreasing sequence, mate. That's what it is. So this is a decreasing sequence. Let's hope we don't just say things in this class. We gotta
Prove it.
prove it. Put a little proof on it. Let's do that. Okay. Okay, so the proof of that is that we want to show that x of n, so we're showing that it's a decreasing sequence, is bigger than or equal to x of n plus 1. That the next term didn't get bigger. It stayed the same or got smaller. And that's what we want to know. Okay, that is, we want to show what's x of n in our sequence? What's that term? 1 over n. We want to show that that's bigger than or equal to the next term. What would be the next term?
1 over n plus 1.
That's right. That's what we want to show. Okay, that's what we want to show. I don't have that. I'm trying to show that. But here's what I'd say. Note, and we want to show this for all, slight omission here. For all n bigger than or equal, for all n element of natural numbers. This is true for all n element of natural numbers. So I want to look back at something. It's your notes. Do you mind?
No, go for it.
Good. Good. Okay, that's what I want to show. Well, here's what I'm going to do to get that result. I'm going to make an observation. I'm going to say for all n element of natural numbers, n is going to be less than n plus 1. Isn't that true? When you look at natural numbers, you look at one of them, the next one's always, if you add 1 to it, it got bigger. Really, what you're doing is you're saying that 0 is less than 1. 0 is less than 1. Do you guys hear me? 0. So if you add n to both sides, you get n plus 0 is less than n plus 1, which just means n is less than n plus 1. Anyway, that's what we have. So now if I divide both sides by n, I'd have 1 would be less than n plus 1 over n. Okay. Now if I divide both sides by n plus 1, remember that's a positive number. 1 over n plus 1 is less than 1 over n. Here I'll finish it up. So for all n elements of natural numbers, here's the statement I get to write. 1 over n is going to be bigger. It's bigger, so it's bigger than or equal to 1 over n plus 1, and that's what we wanted to show. So that's a decreasing sequence. Okay, let's look at another example. Minus 2n is a decreasing sequence. Let's prove that. Okay. Well, we want to show, you know what, let's change this. I don't want to do another decreasing sequence. Let's make it 2 times n. And it's not going to be decreasing, it's going to be increasing. Sorry. An increasing sequence. Make that change. That's what Michael Jackson was saying. Okay, so we want to show that 2n is an increasing sequence. That is, we want to show that x of n is less than or equal to x of n plus 1, and that's for all n known in natural numbers. That's what we want to show. Okay, so what's x of n? X of n is 2n, so we want to show that 2n is less than or equal to, and here's what I'm thinking. You know, what is the term in the x of whatever spot? It's 2 times whatever the index is. Is that okay with everybody? It's 2 times whatever the index is. So here I want to know what is x of n plus 1? Well, it's 2 times whatever the index is. So my answer is it's 2 times n plus 1. That's what I want to show. That's easy enough to show. We again note that n is less than n plus 1. And so if I multiply both sides by a positive number, and this is true for all n element of natural numbers. And remember, we want this for all n element of the natural numbers. So that means that 2n will be less than or equal to 2 times n plus 1 for all n element of natural numbers. So that tells me that 2n is an increasing sequence. Oops, nervous. Increasing sequence. One thing I want you to observe is that our first example is 1 over n, and it was decreasing. And that means it's monotonic, because if it's decreasing or increasing, it's monotonic. Is that okay? And it converged. 2 to the n was increasing. That means it's monotonic. But 2 times n did not converge. Why doesn't it converge? Say it again, Chuck.
Because it's not bounded.
Because it's not bounded, okay? So our 2 examples, we looked at 2 monotone sequences. One of them converged, one of them didn't. Let's look at another example. But before I do, let me just make sure that I write this down. Note, 1 over n is a monotone sequence. Why is it a monotone sequence? Because it was decreasing. So, also, the sequence is 2 times n. That is a monotone sequence. And it's monotonic because it's an increasing sequence. I'll just write this down. Note, a constant sequence is a monotone sequence. You know, a sequence is always the same number. 3, for instance, 3, forever. Each term is 3. It's monotone. It's a monotone sequence, monotonic. Why? Is it monotonically increasing or decreasing? What does it mean to be increasing? It means the next term didn't get smaller. The next term is bigger than or equal to the previous term. If I have a constant sequence, is that true?
It'd be both.
It's both? Is that okay with everybody? It's a monotone sequence. It is both increasing and decreasing, and a decreasing sequence. Okay? Well, not everything's monotonic. Not everything's monotonic. Here's an example. Minus 1 raised to the n, which equals to minus 1, 1, minus 1, 1, minus 1, 1, and so forth, is not monotonic. Okay? Now, for this guy right here, I can see it's not monotonic. When I look at the first 2 terms, minus 1 to 1, what just happened? Did it go up or down?
Up.
It went up. But then to go from the second term to the third term, it went down. So it can't be both increasing and decreasing from spot to spot. Hi, John.
Are you Dr. Williams?
I'm all right. You're here.
I am. Right on time.
Yes, sir. So that's not monotonic. I want you to see that non-monotonic sequence that we just gave, it didn't converge. We know that minus 1 being doesn't converge. Wait a minute. Are there non-monotonic sequences that converge? Well, the answer is yes. So let's look at one more example. So the sequence that's minus 1 over n, minus 1 to the n over n. Let's look at it. The first term we get is minus 1. The next term we get is a half. The next term we get is minus a third. Then we get 1/4. Then we get minus 1/5. What about this sequence? Is it monotonic? Is it either increasing all the way or is it decreasing all the way? Well, to go from minus 1 to 1/2, we went up. But when I went from 1/2 to minus 1/3, we went down. So it's not an increasing sequence. It isn't always going up or not going down. Is it a decreasing sequence? No. So that means that it's not a, that's right, Megan, it's not a monotonic sequence. Now this particular sequence is non-monotonic, but it does converge. Is that okay with everybody? So if somebody says, hey, if you're convergent, you're monotonic, the answer is no. You can be convergent and not monotonic. And we've seen two other examples, or we've seen an example of a monotonic sequence that does converge, and we've seen an example of a monotonic sequence that didn't. So it doesn't seem like monotonic sequences have some kind of specific relationship with being convergent. But it turns out there is a big theorem that does relate the two. And here's what it is. We have one more condition. So it's called the Monotone Convergence theorem. And this is what it says. It says a monotone sequence converges if and only if, so if and only if, the sequence is bounded. It is bounded. Moreover, well, that's a good word. If x of n is increasing and bounded, whoops, gosh, that's really good. Then x of n converges to the supremum of the x of n's. And similarly, if x of n is decreasing x of n converges to the infinimum of x of n's. We're going to prove that. Okay. First thing I notice about this theorem is that it's an if and only if statement. There's two directions. So I'm going to start off with let x of n be a monotone sequence. Okay? Okay, so I've got its monotone. Okay? Now here, what we're going to do in this forward direction is suppose x of n. So Audra, I'm going to suppose, so reading from left to right here to the forward direction, we're supposing that the sequence is convergent. What do we want to show?
It's bound.
We want to show x of n is bound. That's what we got to do. Well, it turns out that was a previous result. We've already proven that. We've shown that every convergent sequence is bounded. We showed that already. So it didn't matter that it's monotone. It's that if it converges, it's bounded. We have already proven that every convergent sequence is bounded. So half the proof we had already done. And if I ask you to prove the monotone convergence theorem, then you can just list that part. You can say, well, it's something we've already done. Okay? Or at least that part of it. So we got to go in another direction. Now we're assuming that x of n is a monotone sequence, okay? And so in the opposite direction, Audra, instead of assuming that it's convergent, we're going to assume that it is, I've erased it, but you can look at your notes. So look at the statement. Now we're assuming that overall for both.
Sorry, it is bounded.
That's right. Okay. So in this direction, we assume, or suppose, that x of n is bounded. So it's monotone and it's bounded. We must show it converges. Show it. Let's say x of n. Okay. Okay, so how do I show this? Well, remember the theorem said more than that. Really, it said if it was an increasing bounded sequence, then it was going to converge to a soup, and if it's a decreasing bounded sequence, it was going to converge to its end. So that's what it said, the statement. But really, when I look back and think about the hypothesis of the statement, the very first thing, as John said earlier, was that the sequence is monotonic. And if you're monotonic, that means you fit into one of two categories. You're either
Increasing.
or decreasing. You might be both. We've seen some sequences are both. What kind of sequences are both? Constant sequences. They're the only ones that are both. Okay. Okay. So here, this splits up into two cases. Case one. Suppose x of n is increasing. You know, we want to show that it converges. And in our definition, to show that a sequence converges, we always have the same standard thing, always the same boilerplate type of fact. We let, yeah, and we're going to need a case that's the absolute value of x sub n minus
X,
what's x?
the limit point.
What is it in this problem? No.
Oh.
We don't know. So for the first time, we have no idea. I mean, we might be symbolizing it by x, but we don't know what it is. The theorem told us what it should converge to. The supremum. But if we had no idea, how would we even guess the supremum? Does that make sense? So here, I know that it's supposed to be the supremum because that's what the theorem told me. Is that okay with everybody? But if we didn't know, if we just said, oh, it just converged, we didn't have that moreover part. We said, well, what does it converge to? And we couldn't even use the definition for convergence because we need to have the x. We don't even know what it is. Have an idea of what it is. That's one of the deficits of the definition. It captures the idea. But if you want to show that the sequence converges, you have to have an idea what it converges to. That's a detriment of the definition. If you don't know, I mean, how do you show that it converges? We're going to get to that later in this course. What other ways can we say? Even if I had no idea what it converges to, can I still show that it converges? Yes, there's something you can do. All right, anyway, right now we know it's increasing. Well, with the theorem says it's supposed to converge to the supremum. How do we even know the supremum exists?
It's bounded.
It's bounded. Okay, so since x sub n is bounded, all right, look. What does that mean? That means there exists an m greater than 0 such that for all n element natural numbers, the absolute value of x sub n is less than or equal to m. So that means, so for all n greater than or equal to n, for all n element natural numbers, that says that x sub n is sandwiched in between minus m and m. So it's bounded above and bounded below. Okay. That's what we have. So m is an upper bound. The x sub n's. Thus, by what, Chuck, does the supremum exist? Why do I know the supremum exists? I know it's got an upper bound, meaning it's bounded above.
Completeness.
Yeah, that's why I'm asking you, because you asked me about it. The completeness property of R, the suit of x sub n exists Yes, sir.
You mean for that to be minus m less than or equal to x sub n?
Yes, I do. Yeah, I sure do. Let's make that change. Sure do. Thank you. I'm saying, it's not every day that they erase the boards or clean the boards for us. And they had cleaned the boards before this time. I was going to get to write on new boards, clean. But that's not what happened. Because one of us came in and before the class started, wrote all over the board. Wrote up the squeeze theorem. Did we not, Megan? Sure did, didn't we? She sure did. So Megan was in here earlier practicing the squeeze theorem, so I didn't come to a clean board. That's okay. Thank you, Megan. I'm just kidding. I hope you keep writing on the board. I was blinking once. Well, that's the supremum of x sub n exists. Okay, I'm going to call it super of x sub n. So I want to show, we will show, that gives us kind of a good candidate for what the sequence converges to. Okay, so I'm going to show that the sequence converges to that. We will show x sub n converges to the supremum of x sub n. Okay? All right, how do I show it? Let's call this something. Let's give it a name. I'm going to call it x star for its supremum, the x, and I'm not just going to call it x, I'm going to call it x star. Because later I'm going to be using the infimum, and I'm going to call it x sub star.
Oh, fancy.
Yes, sir. Well, that's what they did in the book, John. We're like I thought. Hey, you said you laughed at one of my jokes. I'm happy. That's
You
all
had
it
me
took.
convinced.
What's
You had me convinced you were that original.
Well, thanks. All right, so how am I going to show this? Here's what I'm going to do. I'm going to let x on the greater than 0 be given. I got a candidate now for what it might converge to. We need a k. That's a spot in the sequence. It's the number of the natural numbers, such that for all n bigger than or equal to k, the absolute value of x of n minus x star will be less than epsilon. Is that okay with everybody? Okay. That's what I need. All right, well, we'll see. Here's what I'm thinking. I'm going to say, well, notice this. Note, since x star equals to the sup of x of n's. Okay? That means it's the least upper bound. That means it's the smallest thing that is an upper bound for this set. It's the smallest number that's an upper bound for this set. So if you go a little smaller, it's not in a little smaller. If you go a little smaller, it's not in.
It's not upper bound.
It's not upper bound. So here's what I'm going to do. Note, x star minus epsilon is not an upper bound of the x of n's. Okay, so wait a minute. Epsilon is positive. If I subtract a positive number from a quantity, that whole quantity just got smaller than what it originally was. Is that okay? So this guy right here is less than x star. Okay? So this guy is less than x star. I won't write that down. It's less than x star. And we had this lemma that we proved that if you give me something that's the supremum, one of the qualities that it'll have is that if you give me something smaller than it, it's not an upper bound. Or we would say it this way: there exists a guy in the set that's bigger than it. That's what it said, John. So that's what I'm going to write down. Our set is this sequence. Okay. So, look, there's a guy in the sequence. So here's what I'm going to say. Thus, there's a guy in the sequence that's smaller than x star minus epsilon. Okay? I didn't say it. There's a guy in the sequence that is bigger than x star minus epsilon. Because x star minus epsilon is not an upper bound. So it's got to be something from the set bigger than it. Well, how do I describe that guy in the sequence? Well, I'm going to say, thus there exists a k element of natural number. I'm going to describe the spot. There's a spot such that the guy in that spot, such that x sub k, that particular term in that spot, now what do I know about it? It's going to be bigger than, so I'm going to change this. X star minus epsilon is going to be less than x sub k. X sub k is going to be bigger than that non-upper bound. Is that okay with everybody? Okay. Now, since, what kind of sequence is x in?
Increasing.
That's correct. It's increasing. Then for all n bigger than or equal to k, we have x star minus epsilon is less than x of k, which is less than or equal to x sub n. For every n that's bigger than or equal to k. So if you go further along in the sequence, the terms can get smaller if it's increasing. So that's what we have. So, for all n greater than or equal to k, we have x star minus epsilon is less than x sub k, which is less than or equal to x sub n. But every x sub n is going to be less than or equal to, well, every term in the sequence is less than the supreme one, which is x subscript, superscript part. So let me write one more thing down. So for all n greater than or equal to k, x star minus epsilon is less than x k, which is less than or equal to x sub n, which is less than or equal to x star. But I need something bigger than x star. X star plus epsilon. So x star is positive, so I'll go bigger than it. X star is not necessarily positive. X star is something. I'll add something positive to it. That makes the quantity with the addition of a positive bigger. That's where I am. Now let's get some of the items out of the way in that inequality and just look at a particular subset inequality from that. Okay, so here's what I'm going to say. So for all n bigger than or equal to k, the part of it I'm going to look at is x of n is going to be bigger than, so I'm looking down here, it's bigger than this, x star minus epsilon. But yet that x of n is smaller than x star plus epsilon. I'm going to subtract x star from both sides. Here's what we got. We have minus epsilon is less than x of n minus x star, which is less than epsilon. So I subtract x star from all three parts of that inequality. Okay, what just happened? I got some quantity sandwiched in between a positive number and its negative. So that means for all n bigger than or equal to k, the absolute value of x of n minus x star will be less than. That's what we wanted. That means that in this case, the x of n's converge to x star, the supreme. And so of the second half of the proof, the first half, not because we've already done it, but the second half of the proof, we're halfway done. We've done the part where, the case where the sequence itself, we knew it was monotonic. The case we were looking at is where the sequence was not convergent. We were supposed to show it's convergent, but was increasing. We showed it converged. Now, case two is, remember, where we are is we're thinking, okay, look, I know I got a monotonic sequence that is bounded. I want to show that it's convergent. So case two is that, well, if it's monotonic, it could either be increasing or decreasing. Well, it's decreasing now. So what if it's decreasing? I'm going to skip some steps this time. Since x sub n is bounded, then the infimum exists. The infimum of the x sub n's exists. But I'm going to write it down here, even though I'm out of room. Call it x subscript star. What are we going to show? We're going to show that the x of n's converge to this x subscript star. Let me write that down. Got just a few more minutes. Oh yeah, that clock's wrong. We will show that x of n converges, in this case, to x subscript star. And how am I going to show that? Same way we always show it. I'm going to let epsilon be greater than 0 be given. Yeah. We need a K. Element natural numbers, such that for all n greater than or equal to k, the absolute value of x of n minus x subscript star will be less than epsilon. Okay. Well, what do I know about x subscript star? It is the thing. That means it's the greatest lower bound. That is, it's the biggest thing that's smaller than all the terms in x of n. It's the biggest thing. So if you go a little bigger, you're not a lower bound. So here's what I want you to notice. Note, a little bigger would be x sub star plus epsilon. That's a little bigger. It is not a lower bound of the x of n. So there exists a k element natural number, that's right, John, such that, so I'm saying x sub star plus epsilon is not a lower bound, okay? So it's not a lower bound, meaning it's not smaller than everything in the sequence. So there exists a x sub k that's smaller than x star plus epsilon. Okay. Now, since what are we assuming about x sub n's in this case?
Decreasing.
They're what?
Decreasing.
Decreasing, that's right, Chuck. So if we go further in the sequence, the terms got, I mean, essentially, it doesn't have to be exactly this, but the terms will have gotten smaller. That's what I want to hear on. So if you go for, since this is decreasing, further in the sequence, it's for all n greater than or equal to k. Let me write it down here. I want to get it. Now that means that x sub n will be less than or equal to x sub k, which is less than x sub star plus epsilon. We're almost done. 2 more minutes. Don't forget, we're having those study sessions in this room. One Sunday, one Tuesday, one from Sundays from 2 to 4 in this room. Okay. Now, so for all n bigger than or equal to k, remember, x subscript star is the infinity. So that's going to be less than or equal to x of n, which is going to be less than, I'll just say strictly less than, x sub star plus epsilon. That's what I'll write. So I won't keep all the clutter involved this time. Well, look, I tell you something smaller than x sub star. What's something smaller than x sub star? Well, it would be x sub star minus epsilon. Because I'm taking away a positive number, so it got smaller. That's going to be less than x of n, which is less than x sub star plus epsilon. Okay? And if I subtract x sub star from both sides, we get that minus epsilon is less than x of n minus x sub star, which is less than epsilon. So what does that tell me? That tells me for all n greater than or equal to k, the absolute value of x of n minus x sub star is going to be less than epsilon. So that says that the x of n's in this case converges to x sub star. And that's the proof. Okay, ladies and gentlemen, I've taken up enough of your time. Thank you very much.